Hello everyone, Mr. Fawcett here, and we are back with another geometry lesson. This is our third and final lesson in our short unit on transformations, and we're going to talk about symmetry today. So we are going to complete the do now. There's two questions, and you need to figure out the coordinates of the image after the following transformation has been performed. Now you'll notice that there is no coordinate plane here. So if you want to sketch one, you can. I wouldn't make it super detailed, but it could help you decide what the coordinates of the image point will be. So pause the video, take a minute or two to do that, and then come back and see how you did. Alright, so we're going to start with number one, the rotation. And it does certainly help to sketch a graph, at least for most of us, I think. The point A, 5, 11, would be somewhere in the first quadrant, right? Because both the coordinates are positive. So 5, 11 would be A. If we're rotating 90 degrees clockwise, that means we are coming down here to quadrant 4. So A prime is going to be here somewhere. And if we think about our rules, right, we know we flip the coordinates, so 11, 5. But then we have to choose the sign based on the quadrant the point is in. If we're in the fourth quadrant, the x value is positive, so I can leave it as 11. My y value, though, is negative. So my new coordinates of A prime are going to be 11, -5. All right, moving on to number 2. B is in the second quadrant, right? Because we have a negative x value and a positive y value. And we are reflecting across the y-axis, right? That is the vertical axis, which means our point is going to end up in quadrant 1. For reflections, right, the only thing that's going to change is the sign of one coordinate. Here, the y value is staying positive, right, because we're in the first quadrant. So that's going to stay 6. However, the x value is going to be positive as well. So that's going to be +3. So B prime is going to be located at 3, 6. Okay. We're going to move on. We're going to start talking or start having our discussion on symmetry. You can pause the video and take 60 to 90 seconds to write down what your own definition of symmetry is. So you've probably talked about it before in the math class or maybe in some other classes as well. But just write down your thoughts on what symmetry is, and then we'll come up with a more formal definition. All right, so symmetry. A figure has symmetry if there is a transformation That's not how you spell transformation. Transformation such that the pre-image coincides with the image. There's a funny story about coincides. I don't know if I'd ever heard someone say the word out loud. So when I had read it in my head, I had always said coincides. And then I think the first time I taught geometry to a class, I knew what the word meant. I just kept saying it incorrectly. I kept saying coincides, and students, I guess, were giggling or laughing or making fun of me for a while until I realized what my mistake was, and then I was like, oh, you're right. It is probably coincides. That sounds a little bit better. So it is coincides. What that means is just that the pre-image would fit directly onto the image, or the image would fit directly onto the pre-image. So if you can do a transformation and the image lands exactly on where the pre-image was, the figure has symmetry. We're going to first talk about line symmetry. A figure has line symmetry, or we call this reflection symmetry, if it can be reflected across a line so that the image coincides with the pre-image. So let's go ahead down here and talk a little bit more about line symmetry. So I have 3 regular polygons. Regular polygons meaning their sides all have equal lengths, and their angles are all equal in measurement. So what you need to do is draw all the lines of symmetry that each figure has. And you can think about a line of symmetry as splitting the polygon into two halves that are congruent. That's a general way of describing a line of symmetry. So I'll give you the first one just to kind of show you what we're talking about if you're completely unsure, and that's not going to be it. It's a little better. Right, so this would be a line of symmetry because if I reflected the left side over this line, the red line, it would land directly on the image on the right side, and vice versa, right? If you reflected, we can just break it down by a single point, right? If I reflected this point over, it's going to land exactly on that point. If I reflected this point over here, it's going to land exactly on the corresponding point from the other side. And the image would look exactly the same. Right? You wouldn't be able to tell the difference between what I started with and what I finished with if I reflected over this red line. So see if there are any other lines for the equilateral triangle that work, then do the hexagon, then do the square. All right, so we do have some other lines for the equilateral triangle. We have a line that looks, oops, that was my eraser, not what I wanted. Start over. Or really start over. It's a little better. All right, so we have one line there that we came up with. We have a second line here, and we have a third line here. So there are three lines of symmetry for an equilateral triangle. For a hexagon, we have a line here. We have a line here. We have a line here. But we're not done. We have three others as well. Have one here. May run out of colors. We have one here. And we have one here. So any of those lines, if you reflected the hexagon over that line, it would look exactly the same as what you started with. So there are 6 for the hexagon. For the square, we have 1, 2, 3, and 4. So 4 for the square. So 3, 6, and 4. Well, what do you notice about the lines of symmetry compared to something else about these polygons? Well, they have the same number of sides as lines of symmetry, or you could say the same number of vertices, or the same number of angles. There is a special relationship between regular polygons. Remember, these were regular because all the sides had the same length and all the angles had the same measurement. So if I go write this pattern down, for regular polygons, the number of lines, the number of unique lines of symmetry is equal to the number of sides, or we could say vertices. And you could also say or angles actually as well. So there's a third one in there. I think the easiest one to remember is just sides. All right, let's look at some irregular polygons. Irregular polygons are polygons where the sides are all not the same length and or the angles do not all have equal measurements. So I would just sketch in, play with some of these, see if you can come up with the correct lines of symmetry. They may have 0, they may have 3, 4, 5, etc. All right, so let's look at the trapezoid. Looks like it has a line right here, right? If you reflected, I would get C to come over to D, D would come over to C, same thing with B and A, and every other point, we'd have a point here, it would reflect over to here, and vice versa. So that certainly is one line. Maybe you came up with another one. Maybe you said there needs to be a line of symmetry. Oh, I keep doing that. Keep forgetting I'm on my eraser. All right, maybe you said there was a line that went through D and B like that. Well, at first glance, it may seem like that's a line of symmetry, but you can actually see there's a lot less of the figure above the line than there is below. And the two halves would have to be congruent, right, for this to be a line of symmetry. So that is not going to be another line of symmetry. This is the only one for the trapezoids. There is just one for this trapezoid. Let's move to the parallelogram. All right, it looks like there could be a line of symmetry here, right? It looks like there's the same amount of shape on one side as there is the other. And there is. However, this is not a line of symmetry. That's why I said having the same, amount of shape or having the two sides be congruent was an informal definition. It's not the exact definition of line symmetry. Because just because both halves are congruent doesn't mean they're going to reflect onto each other. And let me show you what I mean by that. So if I have a parallelogram, this point in the top right would need to go to, we'll call it the blue point in the top left. However, if you reflected this purple point, well, it goes perpendicular to this red line of symmetry. So it actually reflects over here. The blue would reflect somewhere here. So the corresponding points don't actually reflect onto one another, which means the parallelogram does not have any lines of symmetry. If this is confusing to you, had you have been in class, I would have had a parallelogram cut out in front of you. So what I would suggest maybe is if you want to print out this page again, you can cut out this parallelogram figure. And you can see, is it possible for me to fold the parallelogram so that both sides match up? And again, it looks like it can at first, but as you try different folds, you'll realize that you can't get a parallelogram to fold onto itself, unless it's a special parallelogram like a square or a rectangle. So the parallelogram actually has 0 lines of symmetry. The irregular polygon over here, we call this an arrow, clearly does have one straight vertical, straight through it vertically. So this would be 1. So with irregular polygons, there's no real pattern to be seen with how many sides or how many vertices. You kind of have to just sketch in the lines and see if there's actual symmetry. All right, let's move on to rotational symmetry. A little bit tougher, I think. A figure has rotational symmetry, or we can also call this radial symmetry, if it can be rotated about a point by an angle greater than 0 degrees and less than 360 degrees, so that the image coincides with the pre-image. The angle of symmetry, or the angle of rotational symmetry rather, is the smallest angle through which the figure can be rotated to coincide with itself. The number of times a figure coincides with itself as it rotates through 360 degrees is called the order of rotational symmetry. So I know that was a few different things thrown at you at one time. We are going to go through a couple of examples to clear this up. Because I can't give you a physical manipulative, I'm going to use a software to show you these rotations. But essentially, what you could do if you're at home is you could print out this page again and cut these figures out. So you could cut out the equilateral triangle. And what you could do is you could lay it directly on top of this one. And you could put your pencil right in the center and you could just twist the triangle around, right? So you could rotate it until this vertex went to that vertex, and this vertex would go to this vertex, and this vertex would go to that vertex. And you could play around to see how many times are you able, like how many times does it land on itself before, we could say, before point A goes all the way around. That would be called the order of rotational symmetry, the amount of times that you can get it to land on itself before it gets back to this starting place. Let me show you the software, though, before we start to answer too many of these questions. I think that'll help you out. All right, so we are using some GeoGebra software, and this is going to allow me to just show you the rotation rather than try to have you think about it abstractly. So we have an equilateral triangle here, and I'm going to rotate it. Let's go this way, though, so we're counting up degrees. And we're going to rotate it until it gets back onto itself. We can see that it took 120 degrees for not a full rotation, but for it to rotate back onto itself. So this is what would be the angle of rotation. The angle of rotation for an equilateral triangle is 120 degrees. That's because, right, if I start back at the beginning, as I count up, it does not land on itself again until I get to 120. So 120 degrees is the smallest angle that I can rotate it for it to land on itself, right? And if I did another 120 degrees to get to 240, it lands on itself, and one more 120 degrees to get to 360, where it also lands on itself again. So because it lands on itself 3 different times, by the time it gets to 360, the order of rotational symmetry, is going to be equal to 3. So again, that's how many times you can rotate a figure by the time it gets back to 360. So 3 would be the order of rotational symmetry for an equilateral triangle. Let's go do another one. Talk about the angle of rotation and order of rotational symmetry again. But we are going to do, we'll do a square. So I'm going to abbreviate here. Angle of RS for rotational symmetry, and order of rotational symmetry. So let's see. And you could actually play around with this. I will drop the link. The link is on your notes, so you can go find that and play around with this yourself if you'd like to. On your own time if you'd like, because we're not going to explore the entire demo. So if I rotate, the first time it gets back to itself, it's taken 90 degrees. So 90 degrees is the angle of rotational symmetry. That's the smallest angle that we can rotate through for the figure to map back to itself. If we keep going, right, another 90 degrees, 180, another would be 270, and another one would be 360, if I can get it to stop right at 360. There we go. So the order of rotational symmetry here is 4, because it landed on itself 4 times by the time it got back to 360. All right, shall we do one more? No, I think I'll let you do that one on your own. Here we have a pentagon you can play around with. I think that's the last. Nope, they do give you a hexagon as well. So on our notes, right, you have a hexagon in the center, which you need to figure out the order of rotational symmetry as well as the angle of rotational symmetry. So you can go back to this, go back to that demo, play around with the hexagon example, right, to help you figure that out if the pattern isn't clear to you yet. So hopefully you've paused the video and you've went to figure out the hexagon, because I'm going to put the answers up here now. The order of rotational symmetry for an equilateral triangle was 3. The angle of rotational symmetry was 120 degrees. For the square, order was 4, angle was 90 degrees. For the hexagon, the order is going to be 6, and the angle is going to be 60 degrees. So maybe you're already starting to see a pattern here between the order and what type of regular polygon it is, as well as the angle of rotational symmetry compared to what type of polygon it is. So take a minute or two, see if you can come up with a pattern or a rule to figure out, well, how could we figure out the order if we're just given a polygon, right? Without playing around with the demo and having it tell you, is there a way to just know the order based on what the polygon looks like? Is there also a way to figure out the angle of rotational symmetry based on what the regular polygon looks like? Again, we're just talking about regular polygons where all the sides have the same length and the angles all have the same measurement. All right. Well, let's take a look and summarize this. So the order of rotational symmetry for regular polygons will be equal to the number of sides or vertices. Again, if you also want to put angles too, you can write that as well. The angle of rotational symmetry is a little bit tougher to figure out. If the angle of rotational symmetry for a regular polygon will be equal to the quotient signifying division. So the quotient of 360 and the number of sides or angles. So the angle of rotational symmetry is equal to 360 divided by n, where n is the number of sides or angles the regular polygon has, or again, or vertices. Let's go back up there and talk about that real quick. Right, so the angle of rotational symmetry for the equilateral triangle would be 360 divided by 3, because there's 3 sides, which gives us our 120, which is what we had. For the square, we get 360 divided by 4, which gives us 90 degrees, which is also what we had. And for the hexagon, we have 360 divided by 6, which gives us 60 degrees, which is what the demo gave us, or gave you. So again, for a heptagon or a nonagon or a decagon, those are all polygons with more than 6 sides. You wouldn't have to try to play around with it on your paper. You could just use the formula, 360 divided by the number of sides. All right, let's quickly talk about irregular polygons and their rotational symmetry. So what I would do to help you understand rotational symmetry for these polygons is to, again, cut out, or maybe you have the cutouts when we did this with line symmetry, but print another page of this and cut out those figures and then place them on top of the ones on your paper. So place the trapezoid that you cut out over this trapezoid. Put your pencil in the center, right, and start spinning the trapezoid and see if at any point it lands on itself before A gets back to where A started, right? If it does, well, then maybe you try to figure out that degree, and you certainly count the number of times that happens by the time A gets back to itself. But you can do that for all 3 of these. So pause the video, run through that exercise. It's, again, having these manipulatives in front of you makes it a lot easier to understand. I think having the hands-on opportunity here. So if you have the opportunity to print another page and run through these demonstrations on your own, do that. I think it'll help you fill in the correct answers. All right, so the order of rotational symmetry for this trapezoid is 1. And the angle of rotational symmetry, well, right, it doesn't have one. This doesn't have rotational symmetry. If the order is 1, that means that you have to essentially get it back to where it started before it looks exactly the same. And that means that the figure does not have rotational symmetry. So if you want to, you can put 360 because it would take an entire full rotation to get the trapezoid to map onto itself. For a parallelogram, the order of rotational symmetry is 2. Right? If you rotate this, let's call this point A. If you rotate this 180 degrees, point A will land on this point, and every other point will also map up. So the angle of rotational symmetry is 180 degrees. For the irregular polygon over here, right, you actually have 5. 1, 2, 3, 4, 5 different rotations that map it onto itself. So if there are 5 different rotations, well, each one of those is going to be the same. So we do 360 divided by 5. This gives us 72 degrees for our angle of rotational symmetry. Okay? All right, we are going to stop here. We're not going to talk about 3D symmetry or plane symmetry or symmetry about an axis because that's not the main focus for this unit. That's just something extra that we can talk about if we have time. But this video has gone long enough. I don't want to extend it any further, so we are going to stop here. As always, enjoy the rest of your day, and we will pick up with a new unit next time.